Okay, today I want to discuss, some of the implications of the formal results that we discussed last time. But before I do that, maybe as also was requested in the chat and might also be useful for others, maybe I can recap quickly what we showed last time. Yeah. So what we showed last time, the main point of what we showed last time was to argue that a theory of gravity, and in the lecture last time we were restricting to ADS or to flat space, has a very unusual property. And the unusual property is that, it might sound, well, the physical interpretation is as follows, that if you think of a slice in the space, then you can write down, some observables near the boundary that in fact, a subalgebra near the boundary that in fact is complete in that it knows about everything that happens in the middle of the slice as well. Okay? So as you can see, that's very unusual. It's not true in a theory without gravity, but it is true in a theory with gravity. And this is holographic. This property of gravity is in fact the key to understanding holography, or it's at least the key information theoretic aspect of holography. And so we call this the holography of information. And what I proved last time was a precise version of these results. In fact, the precise results are not proved quite according to this cartoon. Rather, we proved the following results. Yeah? Think of ADS, and this is flat space. Okay. Then the precise result is that if you think of a subalgebra in ADS, which lives in a band from 0 to epsilon, or a subalgebra in flat space, and this lives in a part of future null infinity, which is in the retarded time band minus infinity to minus 1 over epsilon, then it turns out that the elements of this algebra, which you might have thought of as a subalgebra of the full boundary algebra, right? There's also a full boundary algebra, which you might call A, and in this case, sorry. In the case of flat space, comprises observables over all of null infinity. Okay. So the result was that any observable in A in the full algebra can be approximated arbitrarily well in A epsilon. Okay. So this was the result that we proved last time. And in fact, I can also remind you how we proved it and what the key physical elements that went into it were. There were two aspects to the proof. The first was that any state which is of the form n, A is the full boundary algebra, that's correct, right? Which belongs to the action of the full algebra on the vacuum can be approximated arbitrarily well Okay, this is the first result, or it's a sub-result. Okay, so if you start with the vacuum and then you excite the vacuum with all elements of A, that's the same space as you get by starting with the vacuum and exciting elements, exciting the vacuum with all elements of A epsilon. And this requires just the positivity of the Hamiltonian. So it doesn't in fact require anything that's special to gravity, but just requires the positivity of the Hamiltonian. The second result, which is special to gravity, is that the projector on the vacuum is an element of A epsilon. Why is that? This is effectively, this is a feature of the Gauss law. Because what it tells us is that the energy can be measured at infinity. This is not true in a non-gravitational theory. what the Gauss law is telling us is that, you can make a measurement here in this region, and that will determine for you the energy. This is true in a theory of gravity in ADS. In a theory of gravity in flat space, you can make a measurement here, and that will determine for you the energy. That's just the ADM Hamiltonian. In a non-gravitational theory, to measure the energy, you'd have to make a measurement everywhere in the Cauchy slice and integrate. You have to take the integral of the stress tensor everywhere in the Cauchy slice. But in a theory without gravity, but in a theory of gravity, you can just do an integral at infinity, and that tells you, what the energy is without having to make an observation anywhere in the bulk. So this is, now note, if you accept these two statements, we discussed this in some more detail last time, then think of any operator this can be written as okay. And now we use the fact that the projector on the vacuum is an element of the algebra to write this in this form. This belongs to A epsilon. This belongs to A epsilon. This belongs to A epsilon. And therefore, Q itself belongs to A epsilon. Right? Or can be, well, there was a step here where we approximated things arbitrarily well. And therefore, Q itself can be approximated. This is a symbol that we were using last time for approximated arbitrarily well. Can be approximated arbitrarily well by an element of A epsilon. Okay, so this is a very brief, a lightning summary of what we discussed last time. Okay, and today the objective is going to be to discuss the physical implications of this result. However, maybe before I do that, I can ask to see if the proof that I just presented and that we also discussed last time was clear, and if there are any questions about it. Yeah, go.
Yeah, so one of the assumptions, so the ADM is well defined only when you fix the asymptotics. And I think last time you mentioned that to do a good theory of quantum gravity, you need to understand, you need to fix the asymptotics as well. Can you explain about this a bit? So what we mean is that we have to start with well-defined boundary conditions, or there is more to it?
No, that's right. You have to assume that, the metric, there's a region of space where the metric becomes, where the metric is fixed. It becomes that of flat space or becomes that of ADS or something like that. So we don't allow, what we are not allowing is we are not allowing something or some excitation which has infinite energy, which is going to come and destroy the asymptotic region of flat space. So we are not allowing for some situation where, maybe you have ADS and then, after some time it tunnels into something else, it becomes flat space or something like that, right? So that's an excitation. It's not an excitation of the form we usually consider, but we are disallowing those excitations here. And we are saying, look, we want to consider excitations where the geometry far away is fixed. So we are trying to do some integral, including an integral over fluctuating metrics, but the metric fluctuates in the bulk, but does not, the fluctuations die off with some power of 1 over r as you go off to infinity. So that's the assumption that's being made here. I don't know if it's an assumption. Probably that's, I think, the only sensible way in which we know how to do quantum gravity. Yeah, does that help? If there more, I can explain more of the, yeah. Okay, fine. Are there any other questions? Yeah.
Hi. So I mean, it might be a naive question. So I mean, if you have this holography of information, then isn't like information cloned like in two places?
No, it's not cloned because it's the same operator, right? Let me ask you the following question, right? Think of right. Anytime you have a question about this, just think of the Gauss law. You see, in a theory where gravity is weakly coupled, what is the Gauss law telling you? What the Gauss law is telling you is that you look at the integral of t00. Let's just think of something which is like flat space, right? And that is equal to some integral of some ADM Hamiltonian. So let's call this some ADM current. Where this is at infinity and this is in the bulk. Okay? Now, this is not saying that information is cloned. It's saying that this operator is equal to this operator. So if you make a measurement of this operator, you also collapse the wave function for this operator. Okay? So what it's telling you is that information is not localized the way we think naively about it, which is that, look, there's some information here which is different from some information here. Rather, it's telling us that we might need to equate some operators, like this operator in the bulk and this operator here. So we are forced to relate to operators, say they're the same operator, and the constraints of gravity force us to do that. This is not cloning. This is just a statement that two operators are the same. So saying that's not, when you talk about cloning, what you mean is you have two different operators, both of which have the same information. That's not happening here. It's the same operator.
Okay, thank you.
Okay.
And also, like, could you explain this step 2 a bit more?
This one?
Yeah, that one.
Why this is just the Gauss law. It's a statement that if A epsilon is the algebra at infinity, right? So in the case of flat space, it's the algebra near retarded time minus infinity. So retarded time minus infinity is this region here. So the ADM Hamiltonian is in fact an observable as u goes to minus infinity. It's the limit of the Bondi mass as u goes to minus infinity. You can think of it in another way. You see, u is t minus r. So the ADM Hamiltonian is defined as r goes to infinity, right? Where you keep t on you keep t, well, here you also have to take t to infinity, but you take r to infinity faster. And if you do that, you end up in u goes to minus infinity. So you see the ADM Hamiltonian is defined here. In this case, A epsilon is just the algebra on ADS in some time band 0 to epsilon. But at every instant of time on the boundary, you can measure the energy because you just have to integrate some component of the metric. So it's really exactly the Gauss law. In the Newtonian theory, this is the integral of the gravitational flux on a sphere at infinity. And it's really just that statement. Yeah. Now, if the energy is an observable, then what does quantum mechanics tell you? Quantum mechanics tells you that when you measure the energy, what do you really do? What you really measure are the expectation values of its spectral projectors. Right? When I say that, some quantity is an observable, what I really mean is if I measure the quantity, then I will get different answers, and the probability distribution is given by the expectation value of its spectral projectors. One spectral projector is the projector on the vacuum. What does this tell us? It tells us if we measure the energy, what is the probability that we'll get 0? That probability might be 0, right? Or it might be something finite. But that's some physical thing you can do at infinity. You measure the energy, you ask what's the probability that you get 0. And that observable is therefore an element of this algebra because the energy is an element of this algebra. Okay, so that's step 2. And then the rest of it is what I wrote.
Yeah, okay. So this 0 state, this vacuum state lives in the entire manifold, right? Or it's not just in bound?
Yeah, the vacuum state is defined as the state doesn't live, the state is the state of the full theory. So when we usually don't say states live in one place or the other place. We can associate observables with space-time points, but not usually states. The vacuum state is the zero energy state of the Hamiltonian. Okay? And the Hamiltonian lives in the boundary.
Yeah, okay.
But the zero energy state of the Hamiltonian also happens to be zero, it fixes what's happening everywhere in the space as well.
Yeah. Okay, thank you.
Okay. Are there any other questions about this?
Yeah, so we have this question like in the proof of the lemma,
Yes.
at what point, so in the statement of the lemma itself, we are using the term that we can approximate it arbitrarily well. So at
Yes.
what point in the proof are we going from exactness to approximation?
Okay, good. Well, it was here actually, it was the fact that, that's a good point. What we really proved, maybe I'll go back to the slides. Yeah. What we really proved is that you cannot have a finite norm vector that's orthogonal to everything here. Okay? So that's slight, if you can, so, that's where we went from exactness. What we didn't show is that given any state, you could in fact, you could reconstruct the same state by acting with an element of the small algebra. What we really showed was that you couldn't have in the big Hilbert space some vector that left behind a finite residue when you took the overlap with all states in the generated by the small algebra. Okay, so we showed that there couldn't be a state in the big Hilbert space which was orthogonal to all elements of the small algebra. That's why we showed that in fact you could approximate something arbitrarily well. You could try and ask, if you have one state which is dense in the other space, then this is true, right? There is no state in the big space that's orthogonal to all elements of the smaller space. So that tells you can get arbitrarily close. That's why we use the fact that it was arbitrarily close, as opposed to saying that you could really generate something exactly. Is this clear?
Yeah, it's clear. Also, one more question.
Yeah.
Why are we restricting our Hamiltonian to A epsilon region instead of just assuming that it's in the A region?
Because we want to prove that the full algebra can be generated from A epsilon, right? Of course, it's in the A region, but then there's nothing to say, right? What do we want to say? What we want to say is that the full algebra, any element of A can be obtained from A epsilon. So H is an element of A epsilon. That's a physical fact. But A is the full algebra. So of course, okay, H is also an element of A, but then there's nothing, fine. But the key point is that H is also an element of A epsilon, and that is enough to say that A epsilon generates for you the full algebra.
Like, on what basis do we say that H is also an element of A epsilon?
That's the Gauss law. That's what I was just explaining.
Okay, that is the Gauss law.
Yeah, that's the Gauss law.
Okay. Thank you.
Yeah. Is there another question? There was, yeah.
Naive question. So we said that like at any state in the A can be is arbitrarily close to any state described by epsilon. But what about if I pick a random region in the bulk of ADS, not just A? Just like if you go to your previous slide.
Sorry, what's the question? I didn't understand.
So like we're restricting our analysis to A and A epsilon, right? But
yes,
does it include the whole region? But if I randomly take any region in the bulk of the ADS, will the statement still hold?
Yeah. So A is an algebra and A epsilon is an algebra. Notice usually we would say the boundary algebra is the full algebra of the theory because I'm looking at all time. So notice, boundary algebra. In fact, if I look at light crossing time, so A is the set of all observables that you have at infinity. Look here, A here is the set of all observables you have at null infinity. So this is the full out state for massless particles, at least. So it's the full algebra of operators for massless particles. So, it's the similarly here as well. So, we don't want to say anything about bulk algebras because bulk algebras are not well defined in the theory of gravity. But it's a reasonable assumption that the full algebra of operators is in fact the full asymptotic algebra of operators.
So it's like the LSZ formalism we do in usual quantum field theory that we take two asymptotic states and then we're able to compute the scattering matrix, assuming that the Hilbert space in the boundary is the same as in the bulk.
Yeah. The LSZ formula tells you that, if you look at the particular limit of bulk correlators, that gives you the S matrix. Here the statement is slightly different. Here the statement is that if you look at the algebra generated by all elements at infinity, that's the complete algebra. It's kind of clear if you think of causally, right? If you think of a light time, a band of time pi here in ADS, you can in fact get all operators in the bulk if you think of empty ADS just by knowing all operators here, because if you have, you can, that's the HKLL formalism, for instance. It tells you if you give me all operators here, I can get all operators here. Here the statement is that, in a theory of gravity, we don't know what the set of all observables are, but it's reasonable to assume that you look at the set of all observables at infinity, and that's the set of all observables. It's true in any quantum field theory.
Right. It's okay.
Yeah, does it mean that by doing measurements, so once we're using asymptotic region in two different senses here. both A epsilon and A are in some sense in the asymptotic region, right? A epsilon here, however, is at the boundary of a single Cauchy slice. So it corresponds to what an observer far away can do in a small amount of time. Okay, look here. So this is an observer far away, but they're only allowed to wait for this time 0 to epsilon. A is an asymptotic observer who can wait, who has had detectors turned on in the infinite past and will continue to have detectors turned on in the infinite future. So it's kind of obvious, I think, or at least I'm saying it's kind of, it physically seems well motivated to assume that A can indeed determine everything in the universe, because A sits at large R, but has detectors turned on from infinitely far in the past to infinitely far in the future. Okay, so it's kind of clear that A, who's an asymptotic observer, knows everything. What's not clear, and in a theory of non-gravitational theory, it's not true, is that A epsilon knows everything. Okay, what we are proving now is that a detector far away, only by making measurements in a small amount of time, can also determine what's happening in the bulk. And that's the surprising result in a theory of gravity. Yeah. Okay, does this answer all the questions? Are there other questions? There's some raised hands, but I don't know if you asked your question or not. I'm assuming all questions answered. Are there questions more? I'm happy to discuss more if there are other questions. Yeah, go on. Someone raised a hand, right? Yeah.
So just to clarify, is it like then we know about the is it echoing? So sorry.
Yeah, go on. Yeah.
Yeah, it's like we know about capital A in the boundary, and because we know about capital A, we know about bulk also. So we are proving we know about epsilon, right?
Correct. So A epsilon knows everything about A, and that's the precise word. So you're right. We haven't proved something about the bulk. What we really proved is that in the boundary, A epsilon knows everything about A. Now I'm saying, look, that it's kind of clear, or at least it's physically reasonable, that A knows everything about the bulk, because A is all times in the bulk, right? So nothing can, from the bulk, you can't escape A. You have to end up in A. That's what I'm saying. In fact, in flat space,
Okay.
there's a slight subtlety, because A is the algebra on null infinity. So we excluded, in fact, the algebra on I plus and I minus. Okay. That's a subtlety I don't want to get into. That has to do with what you do with massive particles. But I don't want to get into that subtlety here. So in fact, okay, well, let me say it since I said, what we really proved is that the algebra of all of null infinity, you could get near the past boundary. However, well, since people are asking this question, the algebra of all of flat space is not quite the algebra of all of null infinity. You have to add to it the algebra of time like infinity. Okay. Because if you look at massive particles, they end up at start at past time like infinity and end at future time like infinity. So in fact, right now, the result that we proved last class showed that the algebra of null infinity could be squeezed down to a small band. If we want the full algebra, we'll also have to say something about the algebra and future time like infinity and past time like infinity. That we haven't said something about. So in fact, there's a gap in the argument in flat space, which has to do with how you include massive particles, which we will not discuss here. Let me point out in EDS, this problem does not arise. Okay, the answer we had both massive and massless particles. This algebra A knows about both of them. Okay, this is a subtlety which is not crucial for the main part of what I want to say. But it's an interesting subtlety in itself, which has to do with how you deal with massive particles in flat space. Okay, are there other questions? Okay. So I'll assume that settles the formal aspects. So now, what I want to do today is discuss perturbative physical checks of this result. Okay. Because, you might say, we proved some result about operator algebras. But what does that mean? Some result about algebras, but, how do you know that that this is a physical thing, right? So I'm now going to play today, as promised, I'm not going to do anything formal. I mean, I will do some things which are formal, but I'm going to try and say something which is, much more down to earth. Okay. So we're going to play the following game. The game is the following. We'll play the game in ADS. You can play a similar game in flat space, but ADS is kind of nice because it doesn't have, problems with infrared issues. Okay. So this is ADS. And now in ADS, we have some observer. Oops. Okay, this observer can make measurements in 0 to epsilon. So this is an astrophysicist who lives and has detectors that work only in 0 to epsilon. Okay, so the detectors have a Cinderella property. From 0 in the time 0 to the time epsilon, they function well. They're very accurate. You can detect, also quantum gravity fluctuations. But after time epsilon, they turn back into pumpkins. Okay, and before time 0, they are pumpkins. Okay? So this astrophysicist can only determine, can only make measurements in this region from in this time band from 0 to epsilon. Okay. Okay. Now, what's the game that we want the astrophysicist to play? Well, so we have some low energy excitation in ADS. I'll make this a little more precise, but it can be near the middle of ADS. Okay. So the challenge is, I've been telling you, if you make observations near the boundary, you can determine everything that's happening. So challenge is, right, can the astrophysicist completely characterize the excitation? I'll make this a little more precise, but I hope the main physical point is clear, right? So the question is, we have these astrophysicists, they live somewhere far away. Notice these two regions are space-like separated, right? So the astrophysicists are not allowed to wait, for signals to emerge from the bulk. Of course, if signals emerge, then they can determine what these pink dots are doing, right? If they wait for long enough, eventually some light rays will come from here and will hit the boundary, and they can do that. But remember, their detectors turn into pumpkins after epsilon, right? And they're pumpkins also before 0. As I said, their detectors are have the Cinderella property. And therefore, they can only make measurements in this region. And they can't wait, maybe some of their friends who have detectors that are better behaved can wait and determine what's happening here. But these poor guys have to make measurements in this region, and they have to determine, what the excitation is in the middle of ADS. Okay. Okay, so that's the game we are going to try and play today. Okay? And I'm going to actually tell you that surprisingly, the astrophysicists can actually complete this challenge. They can actually do this. Okay, and I'll explain to you how. Okay, let's make this game a little more precise. Okay, so I have to tell you, I'm going to make precise what are the words low energy. Okay, and I'm going to tell you what the abilities of these observers or these astrophysicists are. So is at least the broad aspects of the game clear? Okay, I'm going to make the rules a little more precise as we go along. Okay. So first, let's say something about the low energy state. Is G, I'm going to denote the bulk state by G, okay? And it has low energy. What does it mean to say that it has low energy? It means that if you look at the component with energy larger than some cutoff, the cutoff is actually, something we can determine. It's something you can set for, but it's something you can set, if you want to play this game, you say, I'm telling you that the energy is less than 1/10 the Planck mass. So you could then set the cutoff to 1/10 the Planck mass, okay? It doesn't matter where you set the cutoff. What's important is, if you look at the part of G, which has, which projects onto energy which is larger than lambda, that has very small norm, okay? Alternately, because G is normalized, if you look at 1 minus the projector of G onto all energy is smaller than lambda, that's, the norm of this state is almost 1. That's why 1 minus this is much smaller than 1. Okay? So that's what it means to say that G has low energy. Now, note that we are not saying that G doesn't have any components which have high energy. In fact, if you think about it a little bit, you will see that if you want to make a localized excitation, which is strictly localized, right? It really lives in a region. It must always have some components that have high energy. Okay? So that you can just check. It's a basic feature of the uncertainty principle that if you make a sharply localized excitation, it must have some high energy components. So we don't want to say that there are no high energy components. We just want to say, high energy components are small in norm, and that's fine. In usual quantum field theory, you can make excitations that are strictly localized that have high energy components that are small in norm. Okay. Okay, now I also want to make the abilities of the observers a little more precise. So what is their ability? Well, they can act. So, we'll in quantum mechanics, if you go and ask people in quantum information, what can you do? Well, usually people say you can do measurements for your quantum system. And what can you do? You can, apart from that, you can act with local unitaries. So they can act with unitaries e to the ijx, where x is a simple operator in 0 to epsilon, okay? In this band 0 to epsilon. So x is a simple Hermitian operator. So you take a simple Hermitian operator, and you can act with this unitary. So this is just textbook quantum mechanics. Textbook quantum mechanics tells you if you have a simple Hermitian operator, you can act with the unitary. J is just a number. Okay, we'll need this number, but J is a parameter. So you can scale the operator. The observers have the ability to scale the operator with J and just add it to the Hamiltonian. That's like acting with the C to the ijx. X is an operator that lives in the 0 to epsilon. So their detectors or whatever they have, you allow them to turn on sources, but only sources in this interval 0 to epsilon. Okay. So that's, and then second, there has to be some aspect of gravity here. So far, we haven't said anything about gravity. Second, they can measure the energy and determine the probability of finding 0. What that means is, in quantum mechanics, you always, if you want to make a measurement, you want to determine a state, you always have to have many identical copies of the state. And what these people are able to do is they're able to measure the energy, okay? And they're able to determine, once they measure the energy, they get different answers at different times. And they're able to determine what is the probability of finding 0 because they measure the energy many times. Maybe once they get 1, sometimes they get 10, sometimes they get 100, sometimes they get 0. And they can, by doing that, determine how many times they get 0. And that gives them the probability of finding 0. Okay? Is this clear? Because, a state in the bulk will generally be some superposition of energy eigenstates. And, therefore, there's a meaningful question of what is the probability that you'll get 0. In everything I do, I'm going to set LADS to 1, although it's not going to be important. Okay, so when I said energy is 1 or 2 or something, it's all in ADS units. Okay, is this problem clear? So now the question is, given such a state G, okay, let me also say what they have to do, right? They need to find G to arbitrary accuracy, okay? That's their task. In that, they need to find G to whatever accuracy you want, in that they should be able to produce a state G tilde, so that G tilde, the overlap of G tilde with G is as close to 1 as you want. Okay? Notice this is, by the way, the best you can expect in quantum mechanics. In quantum mechanics, when you have an infinite dimensional space, you can never determine, you can never say I'm going to find a state exactly. Because you have a finite number of experiments, you can always say, look, I found a state, and the overlap of this state with the true state is something you can determine that. Right? So this is so that's arbitrary accuracy, means an accuracy that we tell them, okay, and they need to find G. Okay, is the rules of the game clear? Now I'm going to explain how they can win this game, but is it at least clear, what these observers have to do? Okay. Okay, if there are questions about this, please ask. I'm trying to make this, hopefully it's a fun game to play. But I'll now try and explain how these observers can actually win this game. Okay. Okay, before we play the full game, let's do a warm-up task. Okay, so let's look at warm-up task 1. Right, so before the observers are admitted to the full, the professional league, they have to first solve this warm-up task. Warm-up task is the following: determine if G is equal to 0 or not. Okay. Now you might say, what's the big deal in that? They have to determine if the state they're in is in the vacuum or if it's not in the vacuum. Okay, it's only a yes or no question. Or maybe they can tell us, if there's some overlap with the vacuum, what the overlap with the vacuum is. Okay. So that's the question. This is the warm-up task. It's not the full task. Remember, the full task is to find fully the state G. Right now, they're just asking if it's 0 or not. Now, you might say, what's the big deal? But in fact, let me point out that in LQFT, this is impossible. Okay. So if the observers can make measurements in this time band 0 to epsilon, you can act with a unitary U, okay, which commutes with all operators in this time band 0 to epsilon. Okay. So in particular, if you look at any observable, you do whatever you like. Okay, you measure any expectation value you like in 0 to epsilon in a local quantum field theory in the absence of gravity. And if U is a unitary operator, which is localized here. So in LQFT, there exist unitaries U, okay, that commute with all operators in 0 to epsilon. Okay. What that means is you give me any operator X and this is the same as the vacuum expectation value of the operator because U commutes with the operator. Okay. So this is the statement that in a local quantum field theory, the state 0 and the state U on 0 are completely indistinguishable from the point of view of observers here. Okay, is this point clear? Right. So the state 0 and the state U on 0 are just completely indistinguishable in a local quantum field theory from the point of view of an observer who lives here. Okay? So this task might seem like, it might seem much simpler than the previous task, but it's already interesting because if the observers can do this using some aspect of gravity, that would be interesting because here is something they cannot do in a local quantum field theory. Okay. Okay, now I want to explain how it's actually pretty easy to do this in gravity. So in gravity, the observers win. How do they win? Well, it's very simple. They just measure h and determine the probability of getting 0. Remember, this was explicitly one of the abilities we granted to the observers. Well, what is the probability of getting 0? Well, the Bond rule tells us this is equal to G P0 G. Right? That's the probability of getting 0. That's the Bond rule. Tells us, the answer of getting a certain eigenvalue given by the expectation value of the corresponding projector. Very good. But this is equal to G0, 0G. Mod of G0 squared. That's it. Okay. So you see, the observers immediately know whether the state is equal to 0 or not. Okay. So if G equal to 0, this is 1. If G is orthogonal to 0, this is 0. So already we see how in a theory of gravity, the observers can get some information that is impossible to get in a local quantum field theory. So even this warm-up game where you're just being asked to determine, can you determine if the state is in the vacuum or not? Well, in theory of gravity, the answer is yes, because you measure the energy at infinity and ask if the answer is 0 or not. You have to measure the probability. Okay, note, we're not trying to measure the expectation value of the energy. If you measure the expectation value of the energy, that's not a meaningful thing. Okay? What we have to measure is the probability that you get 0 upon measuring the energy. That is given by the projector on the vacuum, and that immediately tells you the overlap of the state with the vacuum. Okay? Yeah, if G is a superposition of 0 in other states, you'll still get this answer. So you'll be able to see what component of G is 0, what the overlap on 0 is. So if G is like half of 0 plus half of something else, this answer will give you, if it's 1 by square root to 0 plus 1 by square root to something else, this answer will give you half. Okay? So the observers can determine that, the state is 1 by square root to 0 plus something else. So they can determine, in fact, the overlap with 0. And that was a question. There's a question in the chat, which is what if G is a superposition of 0 in another state? It doesn't matter. They still get this answer. So they can still determine what the overlap of G with 0 is. In particular, if G is 0, that overlap is 1. If G is orthogonal to 0, that overlap is 0. If G is neither 0 nor orthogonal, but it's a superposition, you'll get some answer between 0 and 1. But the observers get that information immediately, which they do not have in a theory without gravity. Why is it a drawback of LQFT that we cannot distinguish between 0 and U0? There's a question in the chat. We do not care about unitary equivalences of states, no? No. Sorry. U of 0 is very different from 0. It's an excitation of 0. What do you mean by unitary equivalence of states? If I act with some, like a field here, that creates like let's say I act with a bomb. I explode a bomb in this region. That is a unitary. That bomb will send out some light rays. When we act with a unitary, that corresponds to all physical operations that you can do. So acting with U on 0 is a very different state from the state 0. We do, we never try to equate all states up to unitary equivalences. If we did that, we would find that all states are equivalent to 0, okay? Because you can always take a unitary and go from 0 to some other state. The point in local quantum field theory is that there also exist unitaries of a special kind which commute with all operators from 0 to epsilon. Okay? And therefore, there are some unitaries you can act with that act locally in this region. They send out some light rays, But, these light rays, an observer, as I said, who waited even in LQFT for enough time would be able to determine you acted with a unitary. But an observer who just makes measurements here would not be able to get the information. So when I say you have to characterize the state, U on 0 is a very different state from 0. U on 0 could have, some life form living in the middle of ADS, because you can act with a unitary and create such a life form. Okay? So U on 0 is very different from 0. And the whole name of the game is, can you determine if the state is the vacuum or not? U of 0 is not the vacuum, and in LQFT you cannot. Doesn't this violate causality even though they're space-like separated? Okay, good. I'm going to answer that question. There's a question in the chat, which is, doesn't it violate causality because they are space-like separated? That's a good question. Okay. So I'm going to spend some time answering the question in a little while. But notice this is just the Gauss law, right? So clearly there's no violation of causality that can go on, right? So why is it that this doesn't violate causality, even though this is space-like separated? It's for the same reason that we don't violate causality when we measure the mass of the sun. When we measure the mass of the sun, what we do is we look at the acceleration that the sun is causing to the earth, and using that we determine what the mass of the sun is. Now someone could say, well, what if the mass of the sun suddenly changed? What if it went from being m to being half m? Right? It looks like the Gauss law, which tells you that the integral of the gravitational flux is equal to the mass, is violating causality, because it seems to suggest that if the mass suddenly changes from m to half m, then the Gauss law would know far away that the mass had changed. Of course, we know the answer to that. The answer is the mass cannot suddenly change from m to half m. The Gauss law doesn't violate causality, because the only way the mass of the sun can change is if something, radiation from the sun, emerges and crosses the Gaussian surface. Okay? So in gravity, you always have local conservation of stress energy. Okay? And therefore, you cannot just violate the energy, you cannot just change the energy in some region in some instantaneous fashion. Okay? The energy can only leak out of the Gaussian surface. And therefore, you're not violating causality. And the reason is, in fact, if you look at this unitary, in a theory of gravity, it's important that you can't just act with a unitary here. Rather, the unitary had to have a history. It had to come from here. And when it came from here, it modified the metric at infinity, and that metric at infinity retains information about the energy. So the observer here is space-like separated at this point, if you see where the bands are, but is not space-like separated from the past history of where the excitation came from. And that's the quick answer to why it doesn't violate causality. If you have any, I'll come back to that discussion. But if you have any other questions about this, just for a moment, just think to yourself why it is the Gauss law doesn't violate causality. And it's for this reason. It's because, the energy always has to come from infinity and go to infinity. The same thing that's happening here. Okay? Is there communication of information going on? No, it's the same as the Gauss law. The answer is the same. Whenever you get worried about these questions, you should just think about the Gauss law, right? The Gauss law knows that there's no, the energy has to come from infinity, has to go from infinity. And so really what is happening is, when the matter fell in, it modified, the matter that is currently making up the sun, at some point it crossed the orbit of the earth. It had to come from somewhere else. It made up the orbit of the earth. And when it did that, it permanently modified the metric where we are. And that's what we are measuring now. So we are measuring, in some sense, the fact that in the past, when the sun was formed, that matter came and entered that region which creates the sun. And that's how we now know what the mass of the sun is. So it's not that the sun is communicating constantly its energy to us or sending us signals and information is jumping. It's really that. Okay, so that's the key aspect. And it's really just the Gauss law. If you think of how the Gauss law works in gravity, you will see how, why there's no violation of causality. Okay? But I don't want to go into a detailed discussion of that right now, because it'll take us too far afield. But is this example clear? I think there's one more raised hand.
Yeah. So I had asked the question about the unitaries in the case of the local quantum field theories. So just to clarify a bit more on what my actual query was. So when you say that you can act with this U on a vacuum to get 0, and
Yes.
on the vacuum 0 to get some other state. So when you talk about acting on this state with you, and ultimately our goal is to determine if some arbitrary state G is how close it is to this 0. So
Correct.
wouldn't you simultaneously act on that G with, say, U dagger, since that will be the bra, and you want to measure like the overlap G between G and 0. So now you'll have G U dagger U0.
No. What I wanted to say
that
here
not what's
was that
happening?
the observers, right? So U and 0 could be orthogonal to 0. So what I wanted to say was in LQFT, let me write it here. Zero and U of 0 are indistinguishable. So say G is U0. In LQFT, it will give you the same results for all experiments that you do in 0 to epsilon as 0 does. So you cannot distinguish between 0 and U of 0. So you cannot answer the question, is G equal to 0 or not? Because G might have been U0. You know,
Okay.
there is a state. The state is, and the vacuum is one state in the Hilbert space. I want to ask, is the state G, which is the true state of the theory, is it equal to the vacuum or not? In LQFT, you can't determine 0, the vacuum is, if G was U0, then you would not be able, any experiment you did would be consistent with, the vacuum. So just by doing many experiments here, I can't distinguish between this state and between this state. So clearly I can't answer this question because there are many states which give you the same results as 0.
So you shouldn't be seen as a sort of a basis changer. That is why I was getting confused, I think.
No. Why is you a basis change? It's a change of the state. You act on the state and you change, it's not a basis change. It's a different state, right?
Okay.
You really take a field operator and you act with a field operator on the state. So you create some particles with U. So it's not a basis change, right? You act with e to the I phi. If you want to think of U as e to the I phi of x, x equal to 0. This is not a basis change. This is U. This is a Hermitian operator, so this is a unitary operator, right? This is not a basis change. You really turn on a source, you created some particles.
Right. Okay.
Okay, good. Are there any other questions, sir? Okay, very good. So, good. So we did this. So in what I showed you right now is that in local quantum field theory, the observers can't do this task, but in gravity, they can do the task. Okay, good. So now let's play a different game. Okay, so they already graduated class 1. Now they come to class 2. Okay, so say the observers are told that 0G is equal to 0. Even if they're not told, they can determine this, right? So they can check that the state is orthogonal to the vacuum. If we give them false information, they'll catch us, okay? So now we get the observers to a different class and we say, okay, guys, now we gave you a state and the state is not orthogonal to the vacuum. Why? It is orthogonal to the vacuum. Why? Because, you found it very easy to determine if it was the vacuum or not. So now we're giving you a new state. It's orthogonal to the vacuum, okay? Now, let X be a simple Hermitian operator in 0 to epsilon. Okay, and we define X, the state X, as the action of X on the vacuum. Okay, so this is a state in the Hilbert space. Okay, this is just my definition of the state X. We're giving them some tests, right? So we can make up whatever test we like. Okay, and I'll normalize it. Okay, so I'll normalize it to 1. Okay, so now the observers have to determine, the task is check if G is equal to X or not. Okay, so this is now the task that they have. So they have to check if the state is equal to this other state X or not. So now they're not checking if the state is the same as the vacuum. Now they're trying to check if the state is the same as some other state. What is that other state? Well, I have some simple Hermitian operator in this band. I act on the vacuum. That gives me some other state. And so it's a similar task to the previous task, except the state is more complicated. This X, could create some excitations or create some particles on top of the vacuum. So we are now being asked to check, if the state is equal to this new state or not. Okay? So is this warm-up task 2 clear? So let me again note this is impossible in LQFT. Why? Because in LQFT, X and UX give the same results for all observables in 0 to epsilon, where U is a localized bulk unitary. Same thing that we just discussed in some detail, right? So, X, so if you make any measurement of any operator, let's call it Q, okay? Okay, in LQFT. For all Q, where U is an operator is, that's localized in some region that's space-like separated to this time band at the boundary. Okay. So in LQFT, they can't answer the question because they again cannot distinguish between X and UX. And again, just to say, U is not some basis change or something, U is a physical thing. So you could create some life form in the middle of ADS. So they can't distinguish between X and a state X, which has an additional life form in the middle of ADS. Okay. So in LQFT, this is impossible. But of course, we are playing this game because we're going to win. So in gravity, observers win. How do they win? Well, they do the following. Right? So they do the following. First, act with the source. Why is this possible? This was one of the abilities we gave them. Remember, X was a simple operator near the boundary. So they're allowed to act with a unitary operator. They just act with e to the I jx. X is the same operator that they're being asked to determine, if the state is equal to X on 0 or not. So they act with a unitary. Second, they measure H afterwards and determine the probability of getting 0 to second order in J. Okay. So they can act with the source at different strengths, starting with very weak strength to slightly stronger strength, and then they can play this game, right? So these are both explicitly the abilities that we gave our observers, and they use these abilities to act with the source and then measure H. Okay. Okay, good. Let's do the calculation and see how this gives us the answer that we want. So what is the result of these two measurements, right? The first measurement takes G, whatever the state G is, to e to the I jx G. Is it clear? It's an action. So they turn on a source, whatever the state G was, it takes the source, it takes the, now the state to e to the I jx on G. Right? And they measure the second thing. What is that? Well, they have to measure now in this state the probability of getting 0 in the energy. So that is the expectation value of P0. Okay. So we now have to do a short calculation to determine this. But is it clear why the result of the experiment is given by this, right? Because first you act with the unitary and then you measure the probability. So this is just quantum mechanics and tells you, this is the result of the experiment. Okay. Now is this clear? Okay, excellent. So let's do it. Let's see what happens. Okay. Let's expand out both sides. Remember, we are trying to measure this. Okay. So now we do, we get G 1 minus IJX. I'll just work to second order in J because I don't need to do anything, because I'm only trying to determine the probability second order in J. Tau. Sorry, where is tau? Where did you see tau? Somebody asked a question about tau. It's a J. Yeah. Sorry, I'm sorry. It's a J. I keep saying this every time, but as I said, I'm now old enough that unfortunately it's other people's problem to figure out my bad handwriting. When I was in school, this was a major problem, right? Because when my instructors couldn't figure out if I wrote a J or a tau, they would just give me a 0, because it wasn't their problem. But fortunately, I'm past that stage, so it's a J. Yeah, thank you. Not a tau. Now it's revenge. Yeah, exactly. Yeah. Okay, good. So now we do 1 plus IJX plus J squared X squared by 2. Yeah. Okay, so this is just the expansion that we do, and the high order terms where we don't care, right? That's order J cube. So I just expanded both things. Okay, now let's look at these terms a little bit, right? You see, look at the term that you get that has the G and the 1. So let's say you pick up the 1. Okay. Well, if you pick up the 1, then the G hits the 1 and that hits the 0. But remember, in the beginning, we said that G on 0 was 0. Right? Recall that G on 0 is equal to 0. This was given to us in this warm-up task. So you cannot pick up the 1, right? Because the G on the 1 will hit the 0 and is going to give you 0. So you can only pick up the J. If you pick up the J from this side and you only want to keep track of the J squared term, then you cannot pick up the J squared from the other side, right? Because that will give you J cubed. Same on this side. When you look at this G, you can't pick up the 1 because that will hit the 0. You can only pick up the J, right? You can't pick up, if you pick up the J squared, then to get a J squared answer, you would have to pick up the 1. Right? This is the only way you'd get a J squared answer, by picking up J squared from one side and 1 from the other side. But that's not possible because you can't pick up the 1. Therefore, the only terms you can pick up are this term and this term. That's the only term that contributes to J squared, right? There's a minus Ij and a plus Ij, and this is immediately equal to okay, so we are done. So you see, we won because this is exactly the overlap of G with the state X. So what was the physical experiment here? It was to turn on a source and then look at the response of the energy to turning on that source. There was already some excitation sitting inside the state because the state was not, a vacuum to start with. But I turned on an additional source on top of that. And once I did that, and now I measured the energy, and I found that doing this experiment beautifully gives me exactly the overlap of G with the state X. Okay. So using this, the observers can also do this second warm-up task. Okay, is this clear? Yeah. Okay, excellent. So now we are almost done. In fact, these two warm-up tasks are in fact almost sufficient to completely fix do the full task. Okay. So now I'll give you the full protocol. Okay. So now I'm going to tell you, so now, the observers have done their warm-ups, and now they go to the full protocol. Okay. So first is, given a state G, we first act with some preliminary U preliminary, so that G becomes orthogonal to the vacuum. So that okay, this is actually pretty easy to do. Why is it so easy to do? Because it's very easy to make a state orthogonal to the vacuum. All you need to do is take one qubit of information somewhere in the IDS and rotate that qubit from being up to down, or just do something, just rotate that qubit to some orthogonal state. To make two states orthogonal when you have a lot of degrees of freedom is very easy, because if you rotate one qubit, that's enough to make two states orthogonal. So we act with this preliminary unitary, and we act with it so as to make the state orthogonal to the vacuum. By the way, the observers can always check, if the preliminary unitary has worked, because remember I said in the beginning that it's very easy for them to check the overlap of a state with the vacuum. Okay, so the observers act with the preliminary unitary so that now the state has been become orthogonal to the vacuum. So now we will just assume this has been done. Okay, so now we will assume this has been done. This has been done. And so we'll just redefine G. Okay. So G, we'll now assume in what I'm going to say further that G on 0 is 0. Okay. In fact, I want to emphasize, if they were given some state, it might not have been orthogonal to the vacuum to start with. So they have to act with this preliminary G. And now this protocol I'm now about to describe will work on this state. But because they know what this unitary is, they can always undo it later, at a later stage. So that's why I'll now just tell you how the protocol works for states of this kind. And as I said, you can always reach states of this kind. Okay. Okay, good. So now take some, now, the main point is that if you look at the set of simple unitaries, the set of simple set of Hermitian operators xi in this time band 0 to epsilon, then xi on 0 forms a basis for the Hilbert space. Here we are speaking of the low energy Hilbert space, and similarly we are speaking of low energy operators near the boundary. And so the point is, this is exactly the point that we discussed also in the last lecture. If you look at the set of operators far away, because the vacuum has so much entanglement, the set of operators that you get, by acting with this Hermitian operator in the vacuum, gives you a basis for the full Hilbert space. You can check this very explicitly, by the way. Just take a quantum field theory and look at the set of operators which are far away, and you take some other state, you can explicitly find, in perturbative quantum field theory, what is the Hermitian operator acting far away that acting on the vacuum will give you any state in the Hilbert space. Okay. We proved the statement last time. This was related to this lemma that we proved last time. Here, we don't need to, prove something formal. We are just in perturbative quantum field theory. And for low energy states, this is just something that can be checked. Okay. Of course, it should not be surprising given our discussion last time and given our discussion, of how the positivity of the Hamiltonian and so on allowed you, to generate by the action of any Hermitian operator far away any state in the Hilbert space. Okay. Okay. So you see, if the observers can determine they are done, right? Because if I tell you what the overlap of G with the basis is, you're done, okay? Now, in fact, the protocol, this warm-up task 2 that we had previously, it almost gave them this, but it didn't give them this. What it actually gave them was gxi squared, okay? So it doesn't give them the phases, and all I need to tell you now is how these observers get hold of these phases, okay? And let me tell you how that works. So pick some x0, okay? Use the warm-up task 2 to determine gx0 mod squared. Now we just declare that gx0 is real and it's equal to square root of gx0 mod square. Why is that allowed? Why are we allowed to do this? Because remember, we are always allowed an overall phase of G is completely irrelevant, right? Overall phase of G doesn't make any difference to anything physical about G. So I can always say that the overall phase of G is such that gx0 is equal to a real number. Okay? Notice the relative phases matter. I can't fix gx0 to be a real number and gx1 to be a real number and gx2 to be a real number and so on, because the relative phases are physical. But I'm always allowed to do one overall phase transformation of G, and I can use that to just declare that G on x0 is a real number. Okay? Now, we get G on xi mod squared. But remember, the observers also have the ability to get G on xi plus x0 mod squared, because xi plus x0 is also a Hermitian operator, right? This also they can get. Why? Because xi is a Hermitian operator, but so is xi plus x0, because Hermitian operators are, you can add them and you get more Hermitian operators, right? So just like they can get this using the warm-up task 2, they can also get this using the warm-up task 2. Okay? But notice that g of xi plus g of x0, I'm going to do some simple algebra, mod squared, I mod squared, g of x0 mod squared, okay, plus twice into the real part of gxi into g of x0. Why? Because this is real, right? That's why you only pick up the real part here. This is known. This is known because the observers can do an independent experiment to get this. Okay, this is unknown. Therefore, they can determine this. Now the observers have access to g of xi mod squared, and they also have access to its real part. In fact, that almost determines completely the phase. Okay, this data fixes the imaginary part of gxi up to a sign. Okay, so that leaves behind one sign ambiguity. I'm not going to discuss in this lecture how to fix the sign. It's kind of an annoying thing. But if you are really interested, see on how to fix the sign. But once we've done this, and I assure you this can be done, it just requires, a little bit more work. But you see, we've almost got everything about gxi. We've got gxi mod square, we've got the real part of gxi. Now we just need to fix the imaginary part, and that's something which can be done. Okay. But once we know gxi for a basis, we completely know G. Okay. So in fact, we found a pretty remarkable result, right? To summarize, And this was, I hope not very formal. To summarize, these observers, by making measurements in 0 to epsilon, can completely determine the state in the middle. Okay? So they in fact can meet the challenge that we started out by setting them, which is, can you do observations far away, even though they're space-like separated, and completely characterize the state of the bulk? Okay. Are there any questions about what we said? Some of it might be a little unfamiliar, but I hope it's simple at least. There's nothing I said that involved anything that was, more than just elementary quantum mechanics, turning on sources, doing some simple algebra. If you go back and you do this algebra yourself, you can persuade yourself the algebra is all correct. And there was nothing here. I hope that's, conceptually hard to understand, although you might need to go through the algebra once or twice to persuade yourself. Okay, are there any questions about what we said so far? And I'm now going to discuss issues about causality and so on that were already asked about, differences with classical gravity and other such issues. Yeah. Are there any questions about what we discussed so far? Okay, if there are no questions, then I worry a little bit that maybe again I lost you guys. I hope that's not the case. Let me just recap, right, what we said. This was a game we started with. This was the game, right? We have some, it was really a very physical game we were playing. We have some astrophysicists. They live near the boundary of ADS. They have some detectors and some, some equipment, but the equipment stops working after time epsilon and starts working only at time 0. Okay, so the astrophysicists can use whatever time they have later to process and so on, but the equipment, becomes junk after epsilon and is junk before 0. Okay, so it's exactly like the Cinderella story. Now they are put in some state. There's some excitations, and they have to determine, these excitations in the middle of ADS. Can they characterize what the excitation is? Okay, that's the question we are trying to ask. So, this was a more precise statement. They're in a bulk state. It's a low energy state. Doesn't mean it doesn't have any high energy components, but it's mostly a low energy state. And what these observers can do is their equipment allows them to turn on sources. You can really do this experiment if you had a lab where you could determine fluctuations of the energy in quantum mechanics. This is really the kinds of experiments people do, right? You turn on sources. So you turn on this kind of a source in the set of local operators that you have, and then you measure the response of the system. The thing that prevents us from doing this experiment today is we can't do this step, right? Because we can't measure the energy and determine the probability of finding 0, because that requires us to look at quantum fluctuations of the energy as measured at infinity, which is something which comes with a factor of g Newton and h bar, and that's something that we can't do. Okay? But if we look ahead in the future and we're optimistic about the future to a point where actually we can look at fluctuations of the metric far away, there's nothing in principle that would prevent us from doing this, right? So these are the abilities that they have. Then I said, look, here's the first question you could ask them. Is the state the vacuum, or is there something living inside? Is there some star or shell or bomb inside, or are you in the vacuum everywhere? That's the first question. In QFT, that's impossible to know, because I can create this star by acting with a local unitary source here. And, I would not know here, these observers would not know till light from here reached them, right? But in gravity, I said, well, that's pretty easy. They just measure the energy. Once they measure the energy, they look at the probability of getting 0. If it's the vacuum, that probability is 1. If it's not the vacuum, that probability is 0. Okay, if it's orthogonal to the vacuum. If it's some superposition of vacuum and something else, they get some other answer. But you see, they can answer this question of is it the vacuum or not. Already, this is a pretty significant thing. Then I said, fine, they know it's not the vacuum. Now let's take some simple Hermitian operator. Okay? This simple Hermitian operator, which acts in 0 to epsilon, I define the state x to be this. In fact, in this part, I needed it to be normalized. Later, I was not assuming it's normalized, so I'll erase. I didn't need it to be normalized, but I said it here for simplicity, but let's erase this part. Okay. So I said, look, X is defined as X and 0. And the task for them is now to check if G is equal to X or not. Again, obviously, it's impossible in a local quantum field theory. It is possible in gravity. And they have to do what? They have to turn on a source and then measure the response of the system to the source that already existed and the source that they turned on. Okay. So this is the first step, and then they measure this response. And then some simple algebra shows you that's equal to Jx, this Gx squared. Okay. There's a coefficient of J squared, but that they can determine, right? So you see, they now know if the state, what the overlap of the state G with X is. Now, the key thing to realize is that X, this is the key thing, this forms a basis for the Hilbert space, right? So if they can determine G of Xi, they are done with their task. In fact, the warm-up task that we had was almost complete because, it told us how you could determine G of Xi mod squared. So the rest of the discussion was just how to determine the phase. But, even if you didn't follow that, you see how, you just do this warm-up task for different cases and you already get this information. In fact, you can also get the phase, and I explained how you could do that, but that's a detail, right? So this was the discussion, and the summary is that the observers at infinity, they really have a physical protocol. You act with the unitary, measure the energy of both physical observations to determine what's happening here. Okay. So in gravity, in 0 to epsilon, they have a physical protocol to determine the state. Okay. Okay, good. So now I want to discuss some aspects. Are there any questions about this? Otherwise, I'll discuss some further aspects of this result. Okay. Good. Let me discuss some further aspects of this result. Will the same statement hold for flat space and de Sitter space? Yeah. In flat space, there's a subtlety. The slight subtlety is that you don't have an infrared cutoff. Okay. So in fact, this basis that you're trying to determine things in is infinite dimensional. Right? So, you can't ask for the observers to determine the state completely because that will require them to determine all the low energy components of the state. Rather, you have to say, can you determine the state up to some soft data that you leave undetermined? Maybe you don't determine the very low energy data. And that indeed can be done. And there's a paper by Papadulaki and Chaudhary that explains how that can be done. In de Sitter space, the statement is actually perhaps more subtle. The reason it's more subtle is you don't have observers near the boundary. There's no boundary of de Sitter. And in fact, it's not clear what the statement in de Sitter space will be. It would be interesting to work that out, but it's not quite understood how this physical kind of low energy experiments would work, how you should make sense of them in de Sitter space. Yeah. Are there any other questions? Okay, good. So first question is causality. We already discussed this, okay? So question is information jumping from the bulk? And of course, that would be crazy, right? And of course, the answer is no, right? Why is the answer no? Because, it looks like these observers are space-like separated, right? Because they're making measurements here. So the observers, they live here. And the excitation, it lives here. So you might think, well, look, the excitation or whatever state that they are in, it lives here. But remember that the excitation had to have gone through the boundary. This is true because in gravity, the only way gravity can be consistent is if you have local conservation of stress energy. In middle, must have passed through the boundary, right? Right? Okay, so what is the precise statement? There's no violation of causality because look here, obviously this excitation went through the boundary. So, this same information just stays here and there's no violation of causality. The precise statement is as follows. In LQFT, we can prepare a bulk state and erase all traces from the boundary. Right? So it's, in LQFT, we say if something is space-like separated to us, we don't have any information about it. But, here we are some observers who are surrounding the system, but, it's still space-like separated to us. So we are forming a ring and this excitation lives in the middle of the ring. And, we say, well, in LQFT, we don't have information about it because we can prepare a state in such a way that we just erase traces of it from infinity. And therefore, we have to wait again for light rays to emerge. In quantum gravity, okay, correlators of H and other observables always retain information about the state. So the problem is not one of causality, right? The problem is that, the thing that's conflicting with the usual intuition is not an issue of causality. It's rather what is breaking down is that we usually we just assume this, right? We say, well, I sent in information from infinity, but obviously I can erase all traces at infinity. But who told you that was, that's not some principle of nature that must necessarily hold. And in fact, in quantum gravity, it is, true that correlators of Fecha and other observables retain information about the state. Okay. The existence of local unitaries in LQFT tells you can do this, but there's nothing that says local unitaries have to exist in all theories. In fact, in quantum gravity, they don't. Okay. And I want to say something, maybe you'll think about this later and you might say, well, I'm confused about causality. Okay. So for all questions of causality, just think about the Gauss law. That's sufficient as far as, in my experience, always to answer all questions about causality. Why? Because in the Gauss law, what do? Well, we measure the flux of the gravitational field at infinity. We use that to determine the energy. Well, how did the information about the energy enter the gravitational field at infinity? Same reason, same thing that's happening here. When the matter that was forming whatever was inside went in, it modified the metric. Metric outside has some memory of what went in. I'm not using memory in the way it's used in the GR literature, where it's used specifically for super translations. But here I'm using memory in a more general sense. I'm saying the metric outside has memory. When you send in stuff, the metric outside retains information about what was sent in. Okay. And that's how, so the Gauss law doesn't violate causality. It violates this assumption that you can prepare a bulk state and erase all traces from infinity. Okay. Similarly, if you ever think, what if I changed some information inside? Well, you could ask the same question in the Gauss law. What if I suddenly change some energy inside? Of course, the answer is you can't. You can only change energy inside by sending it in from infinity or letting it go out back to infinity. Same thing here. Okay. Okay, good. So this is what I want to say about causality. I know there were questions earlier. I hope I answered them earlier and now. If there are more questions about causality, how this is consistent, I'm happy to take them now. Are there any questions about this? Okay. Let me say something about differences with classical gravity. So you could say, can you play the same game in classical gravity? Of course, the answer is no, right? That we are not measuring which can also be done in the classical theory. Does this game that we are playing, does it work in classical gravity? And of course, the answer is no, right? Why? Because you think of oh yeah, is that question gone?
Yeah, I'm a little bit confused about the statement that excitation in the middle has arrived from infinity, the infinity. And so it seems to me that we have two infinity. One is the past and the other, the usual one. What is the difference between these two?
Sorry, what do you mean by usual one? This is the
I mean,
infinity of idiot.
yeah, the usual, I mean, like where we have this 0 epsilon and r infinity. Yeah, that's
Sorry,
yeah.
can you say again, please? It's a little unclear to me. You mean the excitation could have come from here?
Yeah, there's a statement that excitation comes from in the middle, has gone from the boundary.
That's right.
So
this is the structure of idiot.
Yeah, it seems to me that this, you mean kind of the past. It's mean like
I mean, how would you prepare this? So imagine that you start with the vacuum in the very far past.
Okay.
So in the very far past, we had the vacuum. Now, how do you create a state that's not a vacuum? Well, you throw in some stuff from infinity. Now you create a state which is not the vacuum.
But this past is a boundary of or ADS, or it's just the past, like. This is my confusion. Like it seems to me
like this past, like infinity. What happens if you go to t goes to minus infinity? Yeah, that's the very far past. Yeah, let's say that's really the past. Okay, so let's set that to be trivial. Okay, so as you take t to minus infinity, we say it was in the vacuum. It doesn't actually matter. This problem of causality, it doesn't matter, because even if the information came from here, it's still causally connected to what's happening here. You have a lot of time for information to propagate out here. Maybe I'm not understanding the question. All I'm saying is something pretty simple. It's a pretty physical statement. Forget about ADS and so on. Okay. In this room, I want to create some. I want to put something here. So let's imagine, in the very far past, there was nothing in this room. I want to put something in the room. I have to send it through the walls of the room. So you can ask the following question: how do the walls of if I look at the walls of the room and I integrate the gravitational flux, on the walls of the room, then I will know the total mass inside the room. That's the Gauss law.
Yeah.
How do you know? You could say, well, the walls are space-like separated from what I'm doing here, right? And so how do the walls know how much energy there is? Well, the answer is this: for me to enter, I had to come in from the door, I had to come in from the walls. And when I did that, I changed the metric near the walls. And that's why that metric always has information about how much energy is inside. When I exit the room, that metric will change. But there's no other way to put in something in the room except for entering from the walls. I cannot just materialize in the room from somewhere else without entering the walls. That's all that's being said here. Now, how does the yeah?
Okay. Yeah.
So that's why I said, whenever you have a question about causality, just think of the Gauss law. Forget about everything I said, right? Just think of the Gauss law. Is the Gauss law consistent with causality, or is it not consistent? Answer is yes, of course it is consistent. And this is why it is consistent.
Okay. Thank you.
Do you see? Because, why is the Gauss law consistent with causality? Because all the information has to come into this Gaussian surface. It has to cross the surface. Otherwise, it would not work, right?
Yeah.
That's how the Gaussian surface always knows about the energy, even though it's might be separated spatially from where the matter is being sourced.
So one more nice question maybe. It's mean that in ADA, or because we're discussing ADA, I think in ADS all the point on the bulk are causal connected with boundary. There is not.
You mean these points? I mean, they're connected,
all
but
the
they're
point.
connected after time. You see, these observers are making measurements here in a short time, but they have to determine what's happening here, but they can't wait for light signals to emerge. This time is usually said to be pi in some units of where LADS is set to 1.
But we are measuring on not in the full boundary, just on this
on a small time band.
Yeah. So the question is like all these points on the bulk are causally connected to this small region?
No, they're not. They're causally disconnected. It's really very physical. Okay, so please don't get just think of the walls of the room. We have detectors on the walls of this room. We have to make measurements. The detectors can only function for, like, I don't know, light crossing time of this is I don't know, 10 to the minus 8, I guess, or maybe it's 10 few meters. So it's 10 to the minus 8 seconds. Okay, but the detectors can only function for like 1 femtosecond. Okay, so we have detectors on the walls of this room. They can only function for 1 femtosecond. That 1 femtosecond is much smaller than the time it takes for light to go from the middle of the room to the boundary. Okay, so the task is, we have these detectors. They're supposed to switch on. They have to do whatever they have to do in 1 femtosecond, and they have to determine what's happening in the middle of the room.
Right.
Okay, that's the game. Of course, if the detectors stay on for a long time, then they can shine light and determine what's happening in the middle. But we are not doing that. We're giving them only 1 femtosecond to switch on and off, which is smaller than the light crossing time of the room, right? Because this room is,
Yeah. So and you say that in summary of this discussion is that this is possible because it seems that always the information was in the boundary. It's right.
Yeah. So I was just explaining why it's consistent with causality that this is possible. Yeah. The fact that it's possible, in fact, requires more analysis of doing our protocol and measuring the energy and the fluctuations and so on, and correlating it with other observables. That was what the protocol was.
Yeah.
But then at the end of this, you could have said, you did this, but how was it consistent with causality?
Exactly.
And the answer is, it was consistent with causality because whatever happened in the middle of the room, in fact, had to eventually come from the boundaries. And so there's some trace or some memory of that remains on the walls. And that's what those detectors are actually picking up.
Yeah, I understand the idea. Thank you.
Okay, great. Okay, are there any other questions? Okay, I also want to explain, as I said, this fact that there's a Gauss law and there's a memory and so on, also true in a theory of classical gravity. But in classical gravity, of course, it is not the case that all information is available at infinity. For instance, right? Remember Birkhoff's theorem. Birkhoff's theorem tells us, consider two spherically symmetric balls of dust. Okay. Then these guys have exactly the same metric far away, right? And there is no way you can distinguish between, if they have the same mass, you can distinguish between a dilute ball of dust and a dense ball of dust in classical gravity. In quantum gravity, just by measuring the expectation value of h, you cannot determine it. In quantum gravity, notice you can distinguish it, and you'll already see a difference if you measure h squared. In this case, h squared is smaller. Why is it smaller? Because remember, if the ball is dilute, if you think of how it is made up of energy eigenstates, it'll have, a smaller spread of energy eigenstates. In this case, h squared is larger, right? Because if the ball is, is dense, you have to superpose a larger number of energy eigenstates in order to do it. Okay, so you see that, the fluctuations of h squared, which are not equal to the expectation value of h squared, This is a quantum mechanical observable. This is not a classical observable. So it's very important that we are looking at fluctuations of the energy and correlators of those fluctuations with other quantum observables. And so in the classical theory, we do not have holography. So classical gravity is not holographic. Yeah. Okay, one more thing that might be, you might say, what about global symmetry? Now, there's a lot of discussion that maybe in theories of gravity, we don't have global symmetry. But in fact, for our purposes, where we are just considering low energy gravity, this is not important, right? Imagine that we have two fields. Phi and phi tilde, right? Which couple identically to gravity. And consider state 1, which is G1. So it's a unitary where you turn on a source of phi, and this is state 2, which is a unitary where you turn on a source for phi tilde. Of course, all gravitational observables for these two states will be the same, because these two fields couple identically to gravity, right? However, I said that you could distinguish these states G1 and G2. Well, how do you distinguish it? Remember, what we measure is in fact something a little different, right? What we are allowed to measure is where this is a unitary near the boundary. These are the kinds of measurements that we looked at, right? Sorry, not psi. Oh, sorry, let me try and charge my laptop. But notice these unitaries can contain phi or phi star. So I can turn on a source that involves phi near the boundary or a source that involves phi tilde near the boundary. So the key point is I'm not only looking at the energy, but I'm looking at the energy after I turn on an additional source in addition to whatever excitation remains. This additional source can break the symmetry between these two states. So if I have the state G1 and I turn on a source that contains phi tilde, that will respond differently than if I had the state G2 originally and I turn on a source for phi tilde. Okay. You can check this in the algebra that we just showed. I mean, I gave you a proof that you could get everything. But physically, the point is it's important that you're not just measuring gravitational observables, but you're measuring the gravitational observable after you have acted with an additional unitary. Okay? Okay, good. Now let me make one last point, which is, or maybe two points. You might be thinking, I use the Gauss law. What about gauge theories? You could say, can you play the same game in a gauge theory? And in fact, the answer is no. Okay? And that's because gauge theories have exactly local unitary operators. For instance, what's an exactly local unitary operator? Well, here is one. You take f squared and you smear it with some function f of r that has compact support. This is exactly local in a gauge theory. It commutes, again, it's an example of the unitaries that we discussed at the earlier part of this lecture. It commutes with all observables in this time band 0 to epsilon. Why do such unitaries exist in gauge theory and they don't exist in gravity? Because gauge theories have both positive and negative charges. Okay. correspondingly, notice that the projector on the vacuum that we've used many times was projecting you onto a unique state in a theory of gravity. However, in a gauge theory, the projector onto zero charge can only project you onto an infinite dimensional manifold of states. Okay? So gauge theories are different. It's because they have positive and negative charges. They're not like gravity. Correspondingly, the fact that states of zero charge are always infinite dimensional, whereas the vacuum is unique in a theory of gravity. Okay? Even when the vacuum is not unique, there are other charges that you can use to determine whether you're in the vacuum or not, which go in. But that's a subtlety that we don't need to look at. But notice in ADS, at least, where we have an infrared cutoff, the vacuum is unique in the theory of gravity, but states of zero charge are not unique in gauge theories. Yeah. Okay, good. So this is the difference with gauge theories that I wanted to say. Let me now say one last thing, which has to do with the difficulty of reconstruction. Is this clear, the difference with gauge theories? Okay, let me make one last point, okay? What about the difficulty of reconstruction for these observers, right? Okay. So our two-step procedure requires A, an action with e to the I jxi, and B, a measurement of h and these together give us gxi mod square. Okay, this was the basis of our physical procedure. Okay. However, if our state G starts to have support on very complex xi, even within the set of operators that are available in the 0 to epsilon, there are some operators, of course, that are simple. Maybe it's like operators which are made of one field, but there are some operators that are more complicated, okay? If this starts to have support on very complex xi, okay, the reconstruction becomes difficult. Okay. Okay, so this is just an explanation of where the difficulty of reconstruction lies. So of course, the measurement of h, you have to measure h as a quantum mechanical observable, and you have to determine the probability of getting 0. That's of course something that requires you to be able to measure quantum gravity effects, because in the end you're measuring h by looking at some metric and seeing how far that metric deviates from that of pure ADS. That's one difficulty. But the other difficulty is that we also have to act with a source, but not all sources are made equal, right? Some sources are easy, some sources are hard. What sources are hard to act with? Well, sources where this operator xi is very complicated. So if the state that we have starts getting support in very complicated xi, then we have difficulty in turning on these sources, and that creates more and more difficulty of reconstruction. In the next and last lecture, I'll come back and discuss the relevance of this for the information paradox, and there I'm going to explain how black holes do indeed have support on very complex xi, and so it's difficult to get information out of a black hole, but it's not more difficult than what one would expect. Okay, so we'll come back to that discussion next time, but let me stop this lecture here, and let me just recap everything I said, and because I think this was an instructive discussion. Okay, so the main point of today's lecture was to say that the results that we proved last time, which were some formal results about operator algebras, well, those results are not just formal results. Rather, they lead to a very concrete physical protocol for how observers far away, we did this in ADS, but in principal observers on the boundaries of these walls could in fact determine what was happening in the middle. And the protocol was basically to do this two-step procedure. You turn on sources and then you measure the energy. And we were able to show that, the way the energy responds to the source that you turn on is sensitive to what the state in the bulk is. And in fact, the way the energy responds to the source determines on what the state in the bulk is. And that in fact is enough to give you this. And because, the set of all sources that you have on the boundary give you a basis for the Hilbert space, this is enough to determine the full state in the bulk. This is an instructive discussion because any question you have about causality, you can ask here. Clearly this is not in violation with causality, just as the Gauss law is not in violation with causality. What is surprising is that it conflicts with a usual intuition that you can prepare states in the bulk, but erase traces from the boundary. And it turns out what this shows us, what this proves, is that you cannot do that in a theory of gravity. So gravity localizes information unusually, but not because, information jumps from one point to the other, but because you cannot erase traces from infinity when you prepare some state in the theory of gravity. This kind of protocol does not work in classical gravity. It does not work in a gauge theory. And as expected, if the state in the bulk becomes more and more complicated, then, it becomes harder and harder to reconstruct it, which is what we have here. Yeah. Okay, so that's what I wanted to say here.